Space. It's the final frontier. Beautiful, vast, and deadly. Beyond the blue shield of Earth's atmosphere, the universe becomes a hostile place. No breathable air, no pressure, bone-freezing cold, or searing radiation. It's a vacuum where life clings to fragile shelters, spacecraft, suits, habitats. But there's another threat, one you can't see, one that passes straight through metal, plastic, and flesh. A threat born in the hearts of stars and flung across galaxies at near-light speed. Cosmic rays. To the average person, the term may sound abstract, like a footnote in a physics textbook. But to astronauts, it's a real, measurable, and possibly deadly concern. So what exactly are cosmic rays? Where do they come from? What do they do to the human body? And as we prepare for longer missions to the Moon, Mars, and beyond, just how dangerous are they? Let's take a deep look at the high-energy bullets racing through the universe and what they mean for our future among the stars. The name is misleading. Cosmic rays aren't rays at all, they're particles. Mostly protons, some helium nuclei, and a smattering of heavier atomic fragments, all stripped of electrons and accelerated to incredible speeds. Where do they come from? Some are born in our own sun, solar energetic particles ejected during solar flares and coronal mass ejections. But the most dangerous ones, the ones we truly fear, come from far more distant and powerful places. Supernovae, colliding neutron stars, even black holes. These events can hurl atomic nuclei across space at nearly the speed of light. When these high-energy particles strike atoms in our atmosphere, they break apart in a cascade, creating showers of secondary particles that we can detect here on Earth. On the ground, we're shielded. Earth's magnetic field deflects many incoming particles, and our thick atmosphere absorbs the rest. But once you leave that protective shell, once you're in orbit or on the Moon or drifting between planets, you're exposed. Out there, cosmic rays come at you unfiltered, unstoppable. Cosmic rays are more than just fast-moving particles. They're microscopic bullets. And when they hit the human body, the results can be profound. A single high-energy cosmic ray can rip through a cell, smashing DNA strands, damaging tissue, or triggering mutations. And unlike many forms of Earth-based radiation, cosmic rays don't just skim the surface. They penetrate deep into organs, blood, and bone. But there's another problem: secondary radiation. When cosmic rays collide with atoms inside a spacecraft's walls, or even within the body, they produce showers of other particles, including neutrons. These can be even more damaging, causing widespread ionization and internal damage. Even short missions in space can expose astronauts to dozens of chest X-rays worth of radiation. On longer journeys, like the 8-month trip to Mars, the exposure is far greater. In deep space, radiation isn't a background risk. It's an ever-present danger. Here on Earth, we live in a safe zone. Not by luck, but by design. Earth is wrapped in a powerful magnetic field, the magnetosphere, generated by molten iron moving deep within our core. This invisible bubble deflects most charged particles, including cosmic rays, funneling them toward the poles where they create stunning auroras. Above that, our atmosphere, hundreds of kilometers thick, absorbs what gets through. By the time cosmic rays reach sea level, their intensity is a fraction of what it is in space. This dual protection is why humans can live, grow, and thrive on Earth without constantly worrying about radiation exposure. But it's also why astronauts, once they step outside this shield, enter an environment for which our biology was never designed. Modern spacecraft are marvels of engineering. They shield against temperature swings, vacuum, micrometeorites. But when it comes to cosmic rays, the challenge is harder. You can't simply build a thick lead bunker. Lead is heavy, expensive to launch, and ironically, it can make things worse. When cosmic rays hit dense shielding, they produce more secondary radiation. That's why spacecraft today, like the ISS, use a careful balance of light shielding materials, such as aluminum and polyethylene, to reduce the radiation load without triggering dangerous particle showers. Even so, astronauts aboard the International Space Station are exposed to about 10 times more radiation than someone on Earth. That exposure increases dramatically on missions to the Moon, where there is no atmospheric shielding, and even more so during interplanetary travel. For a trip to Mars and back, NASA estimates that astronauts could receive a lifetime's worth of radiation in just one mission. This is why radiation shielding is one of the biggest obstacles to long-term human spaceflight. Radiation damage in space doesn't always announce itself immediately. The effects can be subtle or sudden. Some astronauts have reported seeing flashes of light while trying to sleep, caused by high-energy particles striking their retinas. Others show elevated levels of radiation exposure in their blood, which may increase their long-term risk of cancer and degenerative diseases. Over time, chronic exposure to cosmic rays can damage brain tissue, leading to impaired memory, reduced decision-making ability, and behavioral changes. In studies on rodents, similar exposures have caused symptoms resembling Alzheimer's disease. There's also concern about reproductive health, cardiovascular function, and even muscle regeneration. In short, the human body isn't built for deep space, and cosmic rays are one of the biggest reasons why. So what are we doing about it? NASA, ESA, SpaceX, and other space agencies are actively researching new forms of radiation protection. Some involve advanced shielding materials, hydrogen-rich plastics, water tanks, even magnetic force fields to mimic Earth's magnetosphere. Others look to medicine, drugs that might repair radiation damage or boost the body's natural defenses. There's even exploration into genetic screening to identify astronauts who may be more naturally resistant to radiation. On future Mars missions, astronauts may build underground habitats, using Martian soil to block cosmic rays. Lunar bases may use regolith, moon dust, for the same reason. But all of this is a race against time. As human spaceflight pushes farther and longer, we need real solutions to a problem that doesn't sleep, doesn't slow, and doesn't stop at the hatch. Are cosmic rays a threat to astronauts? Yes, but so were mountains to early explorers. So was the ocean. So was flight. Every great journey comes with danger. What matters is how we prepare, how we adapt, and how we protect the people who take those risks on behalf of us all. Cosmic rays are one of the universe's oldest forces. Long before Earth formed, they traveled across space, unseen. And long after Earth is gone, they will still be moving, silently, eternally. But for now, they are one of the last great hurdles standing between us and the stars. The stars call to us. But space is not a friendly place. It is cold, airless, and filled with radiation that can unmake cells and unravel DNA. Cosmic rays don't glow. They don't buzz. But they are there, in every second, in every journey beyond Earth's shield. They remind us that exploration isn't just about courage. It's about caution and knowledge, and above all, respect for the unseen forces that shape the universe. We're learning, we're preparing, and we're going farther than ever before. The question isn't whether cosmic rays are a threat. It's whether we're willing to face that threat in pursuit of something greater. Because beyond the danger lies discovery.